Prof. Good evening, sir.
I say, no, no, the man is just will all good the lady here. I'm no Zoom meeting. Can say my account number. I will advise him Monday. So Marina Pugo. The man. So let him go. 16,000. 16,000. Let them just leave. It's a very stupid, ungrateful man. He didn't care about Baramado, but he can't go to her first. I'll go to if I can and the nurse, it's not enough to you. Then I do my feeding order or more before.
So, bro, we want to start to you can mute yourself. Professor Wakwe, mute yourself. Redmi. Welcome. Who is Redmi? Redmi. Since people are not showing their face,
that's my phone. It's me. It's just my phone.
Eh?
No, it's me. It's me. Balogun is me. Balogun is me. It's my phone. Yes.
Is that Larry?
Yes.
You have transmuted to Redmi.
No, it's because I'm using my phone.
No, that's a transformation now. You can do log transformation. It's transformation.
No, I'll log into my PC when I get home. That one has my proper name. So it won't be like that of a mistaken identity.
No problem.
Well done.
No mistaken identity.
Okay.
Okay, I think yesterday, we can start. Dr. Kayode. Dr. Kayode, unmute yourself.
Hello, sir.
I told you joined yesterday.
I didn't know.
Oh, you didn't know? You were not following the something. I don't need to be listening individual person now. You are not following the thing. You are not following.
I'm very sorry, sir.
Okay. No problem. Okay. Yesterday, I think we stopped at we look at the comparing one mean and one sample t-test where we use an example of people that suffer victim of Ebola. We compare the age distribution of 20 people with a known age a known mean in the population. That is one sample T. You have access to a sample. Of course, when you have access to a sample, you'll be able to know the mean. But you don't have access, it's only one sample. You are comparing your sample with the mean in the population. That's one sample. Then the independent sample t-test, two independent group, you know the mean of the two, you are comparing the means of the two. That's independent sample t-test. Now, we did that also, we compare they lost to absenteeism in two companies, mining and what do I call it? Mining and construction industry. We interpreted the result. So what we want to go directly to today, if we look at the funniest thing is that the interpretation of all of them is the same. The interpretation mean confidence interval. The interpretation of all the comparing two means the same. with their the confidence interval. So it's all the logic behind them that differ. And it's good to. So if you don't know the logic, you will not be able to run it. But when you finish running, the interpretation is the same. It's knowing when to use it now. When to say I'm using one sample t-test and how to use computer to get to that, what to do. Because when you go to compare mean, it gives you the option, one sample, independent, and pair t-test. So here now I want to quickly look at the pair t-test. When do we use it? We use it when there are two experimental conditions and the same participant took part in both. Can be experimental design, but in that experimental design, the same participant took part in both. Like for example, I think Dr. Laiwa and Dr. Balog was raising an issue yesterday. And I said that sometimes if you have two groups, control and experiment, experimental subject and experimental control, and you do baseline, later you now do your experiment and do post-intervention for both of them. So you have 4 groups of sets, 4 groups of data sets. The pre-experimental and control, so there are 2 of them. Post-experimental and control and 2 of them. So there are different, when you at the baseline, you compare the 2. When you compare the 2 of them at the baseline, if you are comparing any means there, you are comparing is independent T because there are 2 separate groups. So when you do your post, both of them, when you are comparing the post experiment, that group and control group, is independent T-test also. But you may want to know, okay, for the experimental group, we want to compare the initial reading with the pre with post. We want to compare post and pre. So in that case, the same thing also for the control, post and pre and post. That is pair for each of them is pair because that experimental pre and experimental post is the same set of people. So in that case, is what you are doing is pair t-test. If you are comparing any mean between them, if the mean is pair t-test. And the same thing you do for the 2. Can you see the 4th data set you do the independent for subject of the experimental and control pre-intervention. You do for them post-intervention. Then you also, after you are done your post-intervention now, you can compare pre and post for the experiment and compare pre and post for the control using pair T. If you are doing that, if you have, that is for quantitative variable, but if there is categorical there, you for the pre and post now, if it is percentage categorical, we are talking of McNema we did last week. McNema and McNema Balka. But this one is comparing me. Can you see the relationship now? So both categorical and quantitative, the way you can do independent, the way you can do paired. So comparing means the second option, comparing means of measure taken before and after intervention or experiment. Yes. Comparing means of repeated measure taken from the same group in observational study. So the study can be experimental or observational. But you just know that you are comparing pre and post or before and after. You can compare means of pair observation, measurement from right and left eye here, corresponding to the other also identical twins. No, this one is not pre and post now. Pre and post, you just take measurement once because those things they occur in pair naturally, like intraocular pressure in left and right eye. You want to compare is pair t-test. Anything you measurement you take. Maybe if we take some people, I learned that in France, French-speaking country, they like taking blood pressure both right and left and separately. If you do, you may do that. If you want to compare right and left, you know that easily left is closer to aortic heart. So that shows that the left they probably have higher blood pressure than the right. So if you want to compare, if you do that, that would be paired because it's in the same person you are taking the measurement from. So the table, we have an example for it. In this table now, show anxiety before. If you look at the formula, I don't want to, because we have talked extensively about the formula for the, so it's good to emphasize, because little thing, if there is not taken, you will see the difference between independent and pair is, look at the formula for independent. You see x1 minus x2. That show that you might have calculated mean, because by x1 minus by x2. These by x are mean, 1 and 2, they are means. They are not individual observation, they are means of the group. That shows that for you, what you are comparing here is the difference between mean. You have calculated the mean of the two of them, you now minus 1 to the other one. So independent theta is looking at difference between mean, two means, difference between two means. Whereas, look at this, bar D means different. So for the data set, you first of all know the difference between the two groups first. It will not be a single. So the way you call talk, you know what is the difference. That is, all the measurement, they are 200. You minus 3 from post or post from 3, whichever way. You minus 1 from the other, and know the difference for all of them. You now calculate the mean of the difference. So what you are doing is mean of the difference. The other one is difference between me. The for pair is mean of the difference. First of all, calculate the difference, or you calculate the mean. So there are two groups of observation there also. But you are not trying to compare the two mean. You are comparing the difference in the reading of the two groups. In the difference, you calculate the mean. So it's mean. The other one, this one is the mean of the difference, while the independent data is different between two means. So look at this one. This shows anxiety score before and after counseling of 9 persons prior to disclosing to them their HIV status. The counseling significantly influenced their anxiety score. So before you before you disclose, you do the score, you give the yes, you score it, you cancel, you score. So you measure their anxiety. So anxiety before and after counseling. So I think we have the data set. Maybe, I don't know, I will reduce the volume. I don't know. Maybe somebody should read. I don't know if it's a prof that way, because, okay, because Dr. Balogun has not settled down. So let me, as you are trying to read, somebody is sending chats. Actually slept off. Okay. Okay. So let me forward this into, as you are trying to share, sir. Let me forward this into Dr. Kaude. Just forward the mail. Who will help us share? Will Prof share for us, Professor Tokeda? The anxiety before and after. That is the name of the file. It's part of the file I shared yesterday. Anxiety before and after.
All right, sir.
Okay,
I will
sir.
do so.
Okay, sir. Because I don't want to be, when it comes to the running of this, I don't want to be the person that will run it. I want people to run it. Yes, that's great. So we can see something now. Anxiety
before counseling.
Well, the score before and after. Before okay. Score before counseling, SBC. Score after counseling, SAC. So before and after. You see that they are entered in parallel, because the same, this number 1 person, whosoever maybe is Joe, is the one that has this 21 before, also has the 76 after. So you will not go and put it after you have entered and entered. That would be parallel. That would be if, let's say, you did the counseling for 2 groups of people separately. You now finish one group B will continue. But this one is the same person before and after. So that is why it's in parallel. But if it is independent group, it will be in series. I think we are getting it now. So, Prof, sir, analyze.
Yes, sir. Okay.
Yes, PLT, yes. So you move the before first, one by one like that. Then the second one after. Yes. Let's click on OK.
So, sir, what is this one supposed to be?
So he's telling you if we have second group, even if we have more, it will be give you the number. We don't have, even if we have more than one variable we want to enter in this data set. That's what I just telling you.
Okay.
Or if you want to another thing, sir. Oh, you have okay. You have already clicked OK.
Yes, sir.
I wanted you to do something. Okay, that's another.
Okay, I can
you want to show. You have to share with us. Okay, you want to do that. Okay, you want to.
Let's do it again.
Okay. Another thing we can put after first now. Put after first. If you don't remove the other one for that space too, click on score after. Score after. Enter it to that space. And I'll put before. It's even good like that. You see what it will do for us. Okay. And share the result with us. Thank you. You scroll to the last, okay? You will see. You see the result. That was the first one you did. This second one you did now. Look at the result. The only thing is the same data set. What it does that the first one is even good like that. That even has the question, sir. The first one, you remove cancelling after from cancelling before. Because the averagely is like the cancelling after before, the anxiety before cancelling rather, they were higher than anxiety after. So when you remove after, that's why the mean, the difference will be is positive. Because most of the something are positive. If you remove the cancelling before from after, can you see now? Because the before is higher than the after. So can you see it's the same value? Just give you negative value. So it's the same thing. So if you look at the deviation, it's the same thing. Standard deviation. If you look at the standard error, it's the same thing. Look at the lower the confidence interval. Can you see? It's the same thing. This one say 15 to 50. This one say minus 50, 50 to minus 15. So we will have something to discuss here. Look at the T. Look at the p-value. So I want to ask if we are following. Among the two, which one is significant, which one is not significant? I want the two results. Which one is significant, which one is not significant?
Both of them are.
Okay. Okay, you say both of them. You can explain, sir, why both of them are.
Because the first one does not include value. I mean a zero, sorry.
Okay.
It's a 50.9 to 14, so it doesn't include a zero. The same thing, if you had drawn a straight line, minus and then zero, it is still within minus. It hasn't got to zero.
Yes, thank you.
So which either way we look at it.
Yes, thank you. The only difference is that it's the same data set. The only difference is that the first one, you remove the smaller value from higher value. The second one, you remove the higher value from small value. Here, let's say 40 minus 90, 90 minus 40. So it's the same, it's in the sign that will be different. One will be 50, one will be minus 50. I think it's very clear now. So, so whenever you see confidence interval, or the mean, minus to minus, it tells you that the difference is still the same thing. What you have gotten is the way you arrange it. If it is okay, we are going, in fact, we'll go back and we run the one we run yesterday on independent T. On the independent, the one with say day lost to this thing. We are going to rerun it. When you run it, you're going to see what I say. Because the way we actually minor the smaller one because the mining was higher than the absenteeism mining was higher than construction. We minor construction from mining because number one was mining, number two, we coded two was construction. We minor 2 from 1. If we have minus 1 from 2 now, we just put 2 first before 1. It will give us the same, exactly the same thing. It's the sign that will be different. It's going to be significant from minus to minus. But if it's not going to be significant, irrespective of the sign of the mean difference, either is plus or minus, the confidence interval will start from minus and end at plus. It shows that it's not significant because by starting from minus and end as plus, it has crossed 0. 0 is one of the possible values. I don't know if you have question in this line. You have question? You can share. Go on.
I mean, just the way the output is, it doesn't show Levin's test this time or
Yes.
test of.
You know why it didn't do that? Let's discuss it because sometimes some things are rather discussed than just saying. If I just say it now, you may forget. And when maybe we are in a conference or we are in a call discussing with the other research colleagues or in a grand round or in a presentation, those are the issues that many people raise. But if you don't, I think we talk about it, you will try to remember. Maybe we discuss it now. So why is it like that? I know that Dr. Kayode may not be able to contribute to that much because he wasn't around yesterday when we discussed this thing. Can we discuss it? You know why it's like that?
That's what I'm wondering. But the one we did before for independence is the test of homogeneity or Levin's.
And if you look at it, say homogeneity or variance, what does it mean? That is, among the different groups, the variance is homogeneous. This one now is not talking about, it's not talking about independent group. That's just it. It's one group. Okay. It's one set of people. I don't know if you understand me, sir.
Yes.
It's one set of, it's just like, it's closer to one sample t-test. It's one group, it's one sample. It's actually one sample. So there's no need to test that. I don't know if you understand, sir.
Yeah, no, it's clear. It's
because
okay.
They are dependent. Yeah. Even the second reading is dependent on the first reading. They depend on one another. Because if somebody scores certain mark now, later it will, it's going to be if somebody scores more than the other person, the next one is likely to be like that also because it's still the same person you mentioned before and after. And that is why it's the same, it's one sample, still one sample. It's only that, it's still one subject. Well, they are independent sample, two samples, they are independent, it's the same. That's why they don't do that. It's only in the independent that you do that. Homogeneity of variance. Any other one? You will see also, the T. The T is -4 here, is +4. It's the same. The T also, the shape is like a normal distribution. It has negative and positive side. It means the same. So toward the negative side, it means that you remove bigger from smaller. If it's toward the right side, positive side, it means you remove smaller from this. So when you see, you don't need to go and quote T is minus. T just put. Maybe we do it. Maybe it's because Prof just said it. If let's say it's only one we did now, and it come out to be negative, like does it change anything? If I want to report it, I will not say the mean is minus 33. I just say the mean is 33. I know the reason is like that. I will not say the T test is minus 4.362. No, I will not say that. But if I want, the only thing I will do is that if I don't say that, instead of saying the confidence level from -50 to -15, I will say it's from you exchange it. If you change it to plus, you exchange it. That is from 15 to 50. I think it's good we discuss this thing very well so that we can understand the way it works. I think we can proceed. You can stop sharing, sir. Prof. Thank you, sir. Okay, Dr. Larry is fully here. So I sent, okay, even that one said, this one I sent. One kind, okay, yes, it's back. So, okay, who do I send? Okay. Yes, I send, yes. Send Bexin inventory. So, Dr. Valo, you can check your mail. I said something on that parametric something. Because the one I sent yesterday when they are on the t-test, where I sent one data file we're going to use on the non-parametric this thing. Okay, maybe that's one which I say I want to forward to Dr. K. Let me just quickly do that now. If you can download, if it's not using phone, because of people is phone, the Dr. K, hope you are not using phone to reach us. Dr. Kari? Dr. Kari? You have to unmute yourself.
Yes, I'm hearing.
Oh, it's not phone you are
Hello,
using.
sir.
Is it phone you are using?
It's phone, no.
Eh?
It's phone. It's phone. I didn't know I would have arranged my system.
Okay, no problem. Okay. And
But
there's no
maybe
need, there's no
subsequently.
point in, okay. I've even opened it. There's no point in rushing to send you data file there. If this thing is hanging, let me just go. Okay, forward. We love it. Anyway, I've ever sent it to you. I've sent the data file and I've sent it to your mail. Okay, let me go back to what we are doing. So now let's quickly look at the assumption. Okay, Dr. Balogun. Dr. Balogun.
Yes, I'm here with you.
Did you see the result you just explained now?
Yes, I was with you. I followed everything.
Okay, that's great.
I followed everything. The depression.
Okay. Now, let's quickly look at assumptions of using parameter. All this one, we assume that all these tests we did, they are all parametric tests. We assume that the data set follow normal distribution. Then you remember for homogeneity of variance, that the variance are homogeneous for different groups. We discussed that yesterday. Data should be measured at least on interval scale. At interval scale means that it should be quantitative. Because if you remember scale of measurement, it's talking about that interval scale. Scale of measurement, nominal and ordinal are used for categorical, while interval and ratio are used for quantitative, numerical variable. So that show is telling you numerical variable. It's not something that is ordinal, and you know ordinal you can give them a number. You can run something and give 1, 2, 3, 4. But sometimes we do use it because those issues, the most important is number 1, followed number 2. The least important there is the last one, followed by number 3. So number 3 and 4 are not so, sometimes you violate it. I think Paul was asking question concerning that one time. Say that if you can decide to say, okay, if sample size is large, if you use Likert scale to do something where you score, you rank people's opinion. If you have large sample size, you can use t-test. Or if you don't even use for it, after you have aggregated, you may have for the Likert scale, you may have about 20 or 10 items. When you now add all the mark together, it becomes big. So in that case now, if the sample size is large, the aggregate score may follow normal distribution, so you can use it. Then independent, that one is the most violated because look at the Pierce time sample. It's not independent. The measurement before and after, they are not independent on one another. So that is why you see that that one can be violated. I will also say that a t-test is a robust test. Even though you violate some of them, it's still valid. And that is why we have the peer t-test. Now, however, there be some situations where you cannot rely on the robustness and say if something is not normal, it doesn't meet all the requirements for using parametric test. It's not all the time, because like now, if it's not normally distributed and the skewness is very high and the homogeneity of variance is violated seriously, you may want to say, okay, I will not say it's robust test. I will not use it. I will now use non-parametric. If you don't want to use non-parametric, I don't know why people don't like to use parametric that will now transform. That transformation is more like academic exercise now, because nobody does that, because it changes the whole story. If like for this data, any of the data, say if you transform log transformation, your arithmetic mean that you have your data, the mean you're going to get for the transform data is not arithmetic mean, it's geometric mean. Geometric, and if you transform the mean back, do antilog, it will not be equal to the mean of your original data. It may be equal to the median, not the mean. So that's why even the natural logarithm is the one that is still better, and it's the natural logarithm I'm talking of. The other transformation, square root transformation, I think we have discussed that before. So let's quickly look at non-parametric counterpart now. Non-parametric counterpart of this student T. The non-parametric counterpart, some of the data sets do not meet assumptions required for parametric test to be carried out. And it's not possible to correct for the problem of the distribution to transformation of data or use of robust test. Dr. Lai, you remember when we're during the session on using SPSS, we try to correct we try to transform some data. You discover that some data are so skewed that when you even transform them, they are not still normally distributed. You remember?
Yes.
In that extreme situation, so you want to resort to using a non-parametric test. So they are called assumption-free tests because all those assumptions are not there. Rather than you trying to calculate mean and you rank. When you rank, you want to see, you make your comparison to ranking. Ranking means that you rank them in ascending order and do some mathematical procedure. Sometimes how those people got the formula, I'm still trying to understand some of the formula, how they got it, but you can have the understanding of the procedure. Then when you get the understanding of the procedure, how can you now use machine to run it? Most of the non-parametric tests work on the principle of ranking. I think I've said it. The process results in high score being represented by high rank, while low score being represented by low rank. That is, when you rank something, you arrange in ascending order, you rank according to their value. So if a particular group, you are dealing with two groups. If the particular group have higher rank, higher values, more than the other group, when you rank, that particular group will take more of the higher rank, while the other one will take more of the lower rank. If there is no more difference in the distribution, if all of them have equal number of low and high score, when you rank it, you see as many that are low in both of them, in both, almost the same number of low value in both of them, almost the same number of high value of both of them. Of course, in that case, you won't see any significant difference. But if one is higher, see that with the one that have really higher score, we have contain most of the rank, high rank, while the other will give most of the low rank. Now, For this one sample t-test, Wilkinson sign rank test. You know, one sample t-test, when you are comparing a mean with a population, I want us to look at the t-test and their non-parametric counterpart. So it's good to know the non-parametric counterpart of each of them. For compare a sample mean with a population mean. One sample t-test, which we did yesterday, then the non-parametric counterpart is Wilkinson sign rank test. Compare mean of two independent groups. Independent sample t-test, student T is the same to the current student T. Wilkinson ransom test, Mann-Whitney Kendall's test. All of them, you just put them there. Is both of them, like Mann-Whitney Wilkinson, is the same procedure that produce it. Just like what will I say? When you have a product and byproduct, you are producing something, two product will not come out. You can have byproduct, you can have the product, also other products along. It's like that. Wilkinson and Mann-Whitney, the same process. You see, when we run it, when we calculate it, the same thing. Is different than mean. It's just a stage that is Wilkinson. When you move further, it's Mann-Whitney. Tell the mean of different in pair observation, like the pair test we just run now. Wilkinson sign rank test. You see the difference between sign rank and ransom. All of them you rank them, but in independent one, for independent sample, after ranking, you sum. You go to see it. The other one you give sign, like plus or minus. Of course, you see the reason you give sign. So this is just a historical background. This Wilkinson test, first developed by Frank Wilkinson, it's an American chemist, in the year 1945. So, you know, if you look at it, the person that described a t-test, Losset, was earlier, 1908. But it's later, people now, how do we use this? This thing cannot be used for non-parametric, for, yes, something I didn't follow. I didn't know that to know mean all the assumption of use parametric test. So that was why this one invented it. So it was popularized by Sidney Segal in 1955. I want us to start with, because I've gone through this, see, I want the situation where we understand it better. Let's start with the independent T and pair T first. The independent T, so the non-parametric counterpart is Wilkinson ransom. Don't worry, when we do it, we go to it, you see why they call it ransom. Data on the substance use and depression. For both pair and independent, it's the same data set I use, but in different way. Look at these 120 participants in this study. They're trying to see how depression is related to substance use. So some people use drugs, 10 people that are on drug, and 10 people that are on alcohol. So we want to compare the depression between the two groups. So you see the depression score of the people on drug and alcohol. But there are two depression scores we did for both of them. The first one was done on Wednesday. The other one was done on Sunday. So in that case, you are trying to compare how the days also affect, apart from the drug, want to see how the days affect both the depression and people on drugs and alcohol, Wednesday and Sunday. You will see on this data now, it shows independent and pair together on the same table. Independent in the sense that if you want to compare depression between two groups, It's there. Between drug user and alcohol user. You see that they are entered in series. After we finish with alcohol, we continue. So that's the way you enter it, even into SPSS, the way it is now. 1 to 10 drug, 11 to 20 alcohol. You can say 1 to 10 alcohol, 11 to 10 AAT drug, doesn't matter. But they are in series. But the depression, if you look at the people on drug are different from people on alcohol. But the depression you see on Wednesday and Sunday is the same set of people. You do their depression on Wednesday, both alcohol and drug. You do their depression on Sunday also. So the same group of people before and after on 2 occasions. So in that case now, it's paired. That one in that context, Wednesday and Sunday depression is paired. But drug and alcohol depression is independent. I don't know if you have question on that. You have question? Or should we proceed? Should we proceed?
Can we call it like between subject by time interaction?
Subject and time interaction.
The between subject and time interaction.
No, why is it between you said? If you say between.
Yeah, because they are independent now, then there is time again.
Within, you said?
I say, well, between and within subject by time interaction.
Okay, which one is between? Which one is between? You are right. Which one is between?
Between is for the independent.
Yes,
and within.
Yeah.
For the parents.
Between drug people and alcohol people, independent. Within both of them, within drug or within alcohol, is the paired. You see within, because it's the same people. Yes, you're right. Any other one? Okay, we continue. So using the data set in the above. So we want to look at all those. So let me just keep it down because what we want to look at is it. It's all those tables we explained there. You will see what would you do now is to arrange. Though sometimes you may not arrange it, then you can, but it's easier to rank it if you arrange it. Yes. In fact, it's better you arrange it. This one is arranged in ascending order. But you must be able to, can you see? After I arrange now, we put below alcohol, all this is alcohol, then drug. Be able to, even though you have arranged it in ascending order, you must be able to recognize which one is in that. So you arrange all of them together. No, there are 20. You arrange it 1 to 20. So you are mixing it together. But you should be able to recognize which one is alcohol, which one is drug. When you arrange, the next step is to rank them, starting from 1. So the number of rank will be based on the sample size of the 2. So if these are 20, you go to have rank 1 to 20. After ranking from 1 to 20, you go to notice that is potential rank. Because some will be the same, like this one as 6. But you give it 3, 4. Because your rank, you just give number 1 to 20. But there are some that tie. This 6, then 35, 35, 35 tie here. There are some that tie. There's where's the. Look at this one. Tie on Sunday, 15, 15, 15, 18, 18, 18, 19, 19, 20, 20. Those are tie rank. So how do you deal with the tie rank? You know, remember in secondary school or in school, any school, if 2 people take second position, there won't be third position, it's fourth position. You cannot, 2 people became second. They score the same mark. You will not have third position, you have fourth position. So it's the same thing. So when you see, you now calculate the average, the rank 3 plus 4, make it 3.5. You now give the 3.5 to you instead of giving this one 3 and giving this one 4. 3.5 plus 3.5. Then you will not say this is 4. It's still 5 position. So here also when you have 17, 17, 17, you add it together and divide by 16, 17, 18 for 35, 35 like this. You now add the 3 together and divide by 3. It gives you 17, which is the average of the 3. You now give 17 to all the 3 of them. So the same thing you do here. Can you see? Where there's a tie 50, 15, with 5 of them. So 4, 5, 6. When you calculate the add together, give you 15 divided by 3, give 5. Give 5 to 3 of them. Look at this one. 16, 16, 16, 4 of them self. When you add the 7, 8, 9, 10 together, divide by 4, you give 8.5. Give 8.5 rank to all of them. Look at this one also, 3. The average is 3, 13. The rank, because 12, 13, 14. So when you add the 12, 13, 14 together, divide by 3, give you 13. The same thing, 19, 19. This rank is 15 and 16. You add together, divide by 2, give 50.25. The same thing with this 20, 20, 17 and 18. So the average is 17.5. So this one is potential and this is the actual rank. Now, you already know which one belongs to alcohol then. You now had, say you are finished ranking now. Now had all the rank for alcohol. And add all the rank for the other group, for the drug. When you do that, it gives you the sum of the rank for each group. That's why they call it rank sum. We can see rank sum. Rank sum. You rank and sum. Now, and this Dr. Larry was, Balogun was asking question in this area. You see the total for each of the, the total for drug for Wednesday is 151. For alcohol is 95. For Sunday, drug is 119. Alcohol is 90.5. Now, Wilkinson statistic is the smallest. The smallest can be for any of the group. The Wilkinson statistic is the smallest value. For in this case now, for Wednesday, the Wilkinson statistic is 95. For alcohol, it just happened that it's in alcohol, the smallest one. Got it right. So the smaller one is in alcohol. For Sunday, it's 90.5. So that is Wilkinson. I said that that particular, the Wilkinson and Mann Whitney, it's the same procedure. So the Wilkinson ended. But while Mann Whitney go further, and now use this formula here, and now put in, but that is using it for the highest group, the highest group that have the highest group, the group that has the highest rank. So the group that have the highest rank now. Okay, well, for a mixture of all of them, the sample size of each of them, N1 times N2, then N1, the one that has the highest rank, is the arrow, is the 1. So N1 bracket N1 plus 1 minus R1 over 2. This is the formula for Mann Whitney U. So when you now feed in, okay, I think I see. I think it's a slip of is it slip of this now. I think it's a mistake in writing. I see what Dr. Balogun was saying. We can try to add it together to really know, is it 95 or 59? So I think he's writing it out. That is a mistake. That's where the mistake comes from. Either 59 or 95. So if we look at the rank for alcohol, the one that is alcohol, now let's see, 1 plus 2, 3, plus this, 3 plus 7, 10, 15, 21, 28, 36, 45, plus 14, 59. It's a mistake. It's a mistake in writing it. I think it's me that made mistake in writing it. It's 59, it's not 95. This one is 59. So I'll change it. It cannot change inside or something. So Dr. Gary, you have seen right?
Yes, sir. Yes, sir. I've seen
It's a
it.
mistake. It's 59. It's not
Okay.
95. It's one. Well, it's no parallel.
Okay,
It's
sir.
parallel now. When you want to write 95, you can't just count and now put. It's 59.
Okay,
The
sir.
smallest is 59. Yes, that 59 is the for Wednesday. That is the Wilkinson statistic. 90.5 is the Wilkinson for Sunday. Then when you now do the McWhitney, 4 is for Wednesday, 5 and 35.5 is for Sunday. Are we together? This one, no, this one is supposed to have left. This table is not supposed to be here. Okay, let's quickly go around this thing. Let's go around it. Somebody can share with us Becksonian depression, Beck inventory, depression inventory. That's the name of the file. Let somebody share with us. Okay. So let's go to analyze. Yes, let's go to 2. No, it's not near me. You go to non-parametric. It's non-parametric, legacy dialogue. You see legacy dialogue. Then you see independent sample team in samples, not team. 2 independent samples. Yes, click on that. So you put yes, depression, yes. Put both of them because both of them. One is for Sunday, one is for Wednesday. Just put both of them. Put both of, okay, yeah. So the substance use is the grouping variable. Put it there. Now put 1 and 2. Yeah, click and put 1 and 2. But that's the way we code it. Click OK. Share the something with us. You share the result, okay? You see the results. You see, McWhitney U. You see, Wilkinson. I'll go and check this there. Maybe it's candor. I don't know this. I'll check what they mean because candor also. If you look at both of them, can you see? For this is for Wednesday. This is for. You will see. For Wednesday, there is different. The difference in their depression is significant. For Sunday, the difference in the depression of the drug and this thing and alcohol is not significant. No, we said that the smaller the value, the more likely it will be significant. You see the one that is significant is smaller, in no respect. Look at the Whitney for Wednesday is smaller than that of. Then the Wilkinson for Wednesday is smaller than this. So before, well, the table, the other one is one of the table. I'm not sure the table I put there. You know, before you have to go and check in statistical table. You can check in statistical table to really know what the critical value for that sample degree of freedom that is for the number, the sample size. What is the critical value to know? But we don't need that. We don't do that now. Once you use computer give you the p-value. You know you can quote the p-value because when we were using the table, you cannot even know the p-value. You can only say that from the table, the p-value should be greater than 0.05 or it should be less than 0.05. That's what you know. You don't know actual p-value. So, but now you can give us the computer give us the probability straight. I don't know if there's any question.
There's correction for ties. There's one B, a correction for ties, not corrected for ties.
Not corrected for ties. Usually is the p-value. If you look at the exact significance, look at the significance. That's what that B. Can you see now? Is it not corrected for ties? So that maybe the other one was corrected for tie. This one, the first one. If you look at it, now, the tie rank. But now I don't know what the procedure for correcting for. I mean, mathematical procedure for correcting for the tie. Maybe I'll go and check it. They just because those are the things they keep on, adding. Keep on adding. I will check. What does that actually mean? But we know that tie, we talk about tie rank. We talk about it because there are some rank that are tie. Anyway, I think we corrected for ties. If you look at you, if we didn't correct for tie, we've used the first potential rank.
That's what I'm thinking of. That the potential
if we
rank
didn't correct for tie, we'll use the potential rank. So if you correct, if that shows that is more likely or less likely to be significant. If you
they are the same.
If you didn't correct for, it's not the same because look at the p-value. 0. It's only this one that is 0. So but look at this one, 0.269 and 0.289. Which one is more significant? The smaller one is still more significant, even though both of them are not significant. The smaller one is still more significant. So if you did not correct for ties, it will be less likely to be significant. You understand me now? You correct them for the ties, it will be more likely to be significant. That's what it's showing us. Any other question? No question.
Can you go back to that Mann-Whitney formula? What's the difference between the small n and the big N? Maybe I
let's
lost something along.
Let's look at it. Because we saw video, we can see. Let's unshare, sir, so that we can go and look at it. Unshare, sir. Thank you, sir. Wait first, let me correct something. Ole. Yeah. Okay, let me. If you look at it, I mean, if you look at it, sir, you see that
Yes.
when you look at what we put in, each of them is 10, N1, N2. So this big N is telling you that the one that has that group that has the highest rank. Yes, I'm not. It just tell you, if you look at it, they say N1 and N1 here, plus 1. So it happened that both of them have the same sample size anyway. So the group that has the highest rank, I don't know if you understand me now.
Okay.
If the other, yes, you now put the N, which is 10 into 10 plus 1, making 11, minus this. So find out the reason they use all those things. Any other question? Any other question? So we proceed. So look at the result. Oh, well, the result we have seen. So that's what we do. Let's look at the other one. This is the non-parametric counterpart of dependent pair t-test. That is Wilkinson sign rank test. We just finished rank sum now. We just finished sign rank sum. We know the reason from the procedure. You were able to know that the reason they call it rank sum is that they rank it and they now sum the rank. They arrange in ascending order and rank it and now sum the rank for one group and sum the rank for the other group. That's all. We can see the one that had the smallest rank sum is the statistic. That's the statistic. But my witness go further to calculate using the sample, the two sample sets, and the one that has the highest higher rank. Okay, but this one is sign rank. You see the reason they call it sign rank. So I think we have discussed the reason behind it, the logic behind it, before and after. And look at it. If we are interested in the change in depression level within people, well, our process within, for each of the two drugs, we now want to compare the depression score on Sunday to those on Wednesday using Wilkinson sign rank test. Look at the way the procedure is. Look at the way the procedure is. Now, you will see what you now do now, this is, the first column is Sunday, Wednesday. You remove the two. The difference, if you remove Sunday from Wednesday, this is the difference. You will see where they are the same, the difference will be 0. Sometimes you are removing this from this. If what you are removing is smaller than the one you are removing from, it gives you plus. If is Bigger, you give you minus. Can you see in this
Bigger.
place now? Yeah, it give you, when it is bigger, it give you minus. When it is smaller, it give you plus. So you're going to have different. So two things and we will observe on this table now. The sign, the plus, or the one that have positive different or negative different. That's where the sign come from. Now, the one that tie, that is pre and post tie, the difference will be 0. You exclude it. And you remember, it's like the logic of when we're doing, you know, that one also is pre and post. When we're doing McNema, yes, I mean, the category, when it's yes before and yes after, you don't do anything with it. Because that thing has not experienced any change. Before and after, if it's yes before, yes after, you don't do anything. If it's no before and no after, all those ones, you don't do. Those are concordant. We said it that time. It's the same thing here. When these values are the same, so you exclude it. It's not useful for that calculation. You can see. So you now rank irrespective of the sign, either positive or negative. You rank the value. You understand me now? You rank the value. For drug now, look at it. The smaller one is 6. Apart from, no, we have excluded 0. Number 1. The next to 6, at least we have 2 13. 30, 13, they tie. So instead of writing 2 and 3, 2 for 1 and 3 for 1, you write 2.5. You have 2 and 3 divided by 2, 2.5. Does it make sense? Now, anywhere you see all those summaries, the tie. Look at 15 also, tie. 15, 15. So it's good, and it's number 4 and 5. Rank 4 and 5. So now the both together now 4.5. I think those are the one that this is. Now, the same thing you do here. A lot of time, this rank, here you put the sign, here you put the ranking, irrespective of the sign, you rank it irrespective of the sign. So you remember the potential ranking. Like for this one now, 7, 7. They are number 3 and 4 in the ranking. Because the smallest is 2, which is 1. 2, 6 is number 2. 7, 7, number 3 and 4. So it will be 3.5. The same thing, 8 is number 5 and 6. 8 here, 8 here. So the rank will be 5.5 for each of them. So that's the way you do it. So you now come. You want to know, look at the positive rank. It happened that all this one here, they are positive rank. You now add all of them together, it gives you 36. Of course, no negative rank is 0. Now, this one, the positive rank is only 1 here. This 8, that has 8, this 8. Then the negative rank, I hold this one, you hold it together, making 47. See? Here now, the negative rank is smaller. Here, the positive rank is smaller. So for drug, positive rank 36, negative rank 0. T negative, total negative, total. For alcohol, total positive 8, total negative 47. So the test statistic is the smaller of the two values, 0 for drug and 8 for alcohol. Do we see that? So let's run it. No, this is just some logic. some logic they just use, and okay, let's run it. Let somebody share it now. Yeah, I think okay. Okay, let somebody share. I think I know the where I have problem. Let somebody, okay, let me share this one. Let me start sharing this. Okay, it's the same. Let's use it. The person that shared that just share that something. The data is the same data set. Now, you have to first of all, you know that we're doing it separately for drug and for this thing. So what you do now, you go to what do I call it? No, go to data first. We split it. Because if you don't do it, you run everything together. That's I remember that was what I put there, which is done. Let's go to split file. Who is doing it? Is it Dr. Larry and Dr. Balogun or Prof? Who is sharing? Who is doing the sharing? Wait. Who is doing the sharing? Unless you unmute yourself, I will not hear you. Okay, Dr. Balogun is not even on board now.
Okay, I'm the one doing, sir.
Okay.
Yeah.
So we go to data. You know, there is something how to split. But I've forgotten. How to split. We did it when we were talking about split here, split file. Now, click on compare group. Compare group, yes. Move the substance inside. Substance use, yes. Yes. Click OK. So that it will do it both, separately. This pairs something separately for drug and alcohol now. Okay, let's go for analyze. Analyze, sir. It's not going. Analyze. We are not seeing anything, are we? Prof, analyze. Go
Okay.
analyze.
Yeah.
But we are not seeing. I'm not seeing. It's not showing up. Maybe you and share. Share again.
Okay, new share.
New share because we are not seeing it.
Okay.
We are not seeing your cursor and go to analyze.
Is it in now?
We are not seeing no.
It's not going there.
If you new share, you have to double. Yeah. Okay, stop sharing then. Stop sharing. What's happening?
Okay, I can start again.
Okay.
I think it's this one.
Yes. Yes. Okay. Go to analyze. It's showing now. Yeah, no problem. Legacy. Related sample. 2 related sample. Yes. Know the way you did it that time. Yes. Okay. Let's just say okay.
Independent sample.
No, 2 related samples. It's not independent. It's pair now. Pair 2 related samples. You're welcome. Yeah. Yes. Okay. Scroll down very well, sir. Welcome. Scroll down so that we can see. Yeah. So you can see that the difference between, you can see drug, the difference between Sunday and we on now. So
Sunday and
you see,
Wednesday.
you see, yeah, the difference between Sunday and Wednesday for drug is significant. For alcohol, is also significant. So if you want to see your intermediate this thing, if you look at positive rank, look, I give you negative rank, positive rank. No, we said it the other time. 36 sum of rank, 36 and 0. For alcohol, 8 and 47. Can you see? So the Wilkinson for both of them is 0 and 8. But if you go further to get the Z, it's one funny formula like this. Maybe I will share it with you tomorrow to calculate this Z from the value of Wilkinson. So if you look at it, both of them are, because if you look at 0 and 8, I will show you a table, a significant table, the statistical table. When I show you, see that for certain the degree of freedom, for lower one, something like 11, you will see it. So you now know that 8 and 0, they are very small enough to be significant. If you remember, the other one that was significant was the 1 4. 35.5 was not significant. So you see that from the something, both of them are significant. Does it make sense? So sometimes when you even run this, you just go and look at the p-value. You don't want to bite your tongue. Just look at the significant 0.001. Then not significant. The other one is significant 0.047. Any question? Any clarification? Any clarification?
Well, just to say that this one doesn't show confidence interval band.
Yeah, it doesn't show it. If you look at it now, you know, this you cannot show it because this one has no, it's not actually calculating. It's just ranking and summing. If you look at it, there's no serious calculation. This was a lot more like a logic, just like the way this one is like a permutation. I don't know if you understand now. This one is like permutation. It's not actually calculating anything serious. You know. So because see, the reason is very simple. If you look at it, the value themselves, they don't go into calculation here. The value. You understand me now? The value they said, those things. So okay, when you rank, you are not summing rank. So do you get the vision now? So most of the time, maybe when the ranking issue, maybe somehow, by the time you look at the what do I call it, the sample size, and most of the time also the non-parametric, the thing that will not follow normal distribution, they are usually small sample size. Something that will be skewed as so they are more useful for even small sample size. So there is no serious. Dr. Balo wants to ask a question.
Yes, I'm just looking at various ways by which you can interpret this table. Will it make any statistical sense to say, to now compare drug and alcohol and treat them like an independent sample?
Yes, this one now is just that we decide to run drug and alcohol. This one is not looking at drug and alcohol. This one we just run. It's just looking at depression caused by drug on Saturday and on Wednesday, comparing the two. You also do the same thing for alcohol. Do you get the picture now? Why we run them together now? That's why we split them. They are just two different things here because they are on the same they are on the same data set. I don't know if you understand.
I understand. I'm just asking whether it makes statistical sense. So now compare drug and alcohol and see whether it is more significant with drug or something like that.
Okay, yes, well, you can say that because it appears that the gradient is more significant with drug than in alcohol. Because if you look at the alcohol own, the p-value is 0.012. No, the drug own rather is 0.012, while for alcohol is 0.047. Does it make sense?
Acting Managing Director Joy Nunez arrived late for the hearing and was asked to speak with the.
Something is talking somewhere.
When abuse.
Is it from Professor Tokiden? That you're okay? I think you can stop sharing, sir. Yes, there's something. Dr. Balogun, we discussed something yesterday that I said I wanted to use that skin lesion to run. What was it? Okay, standard error. Yes, I want you to share that skin lesion file. You are the only one that have it here. Share the skin lesion file. Okay, thank you. So I want us to go to me. Okay, is it Excel you are sharing now? This is Excel. This is not the SPSS. Hello, sir. Hello, Dr. Balogun. Dr. Balogun, I cannot hear you unless you unmute yourself. Dr. Balogun. Dr. Balogun.
Yes, can you hear me now?
I can. Yes, you are not. I said this is
Sorry,
Excel.
I need to take it to SPSS.
It's not the Excel. I want you to through the. Don't you save it? Didn't you save it as SPSS that time?
I can't remember.
The S is there. It's there. The SPSS is there.
Okay.
And it's Excel. What you do is that you open SPSS, or where you save it, you see the SPSS and just click on it, or you open SPSS and go and look for it. So
Okay.
I don't want us to be. Otherwise, if you want to do it, or if you cannot see it, open SPSS. When you get there, if you get to the file where you pick this Excel, now click on look for SPSS, or I will tell you what to do so that you pick it as SPSS. And now you remember the way we did it now. If you want to import Excel, no, I don't want. Let's just do it like that. So if you want to, if you cannot see where you save it as SPSS, you know that one importing Excel is not part of this. But let's see, you can benefit from it. So you can stop sharing this one and go and look for. And first of all, open your SPSS. Stop sharing this one.
Let me just stop here. Let me look for the SPSS.
Look for that. Okay.
SPSS.
The SPSS is there. Yeah.
Mm. I don't know.
You are not seeing it, right?
I'm trying to check my folder now.
Okay.
It's
And maybe I should
here.
do. Maybe I should use my own. Then maybe I should. Maybe I should read it from here. Then.
Let me import it.
Maybe I should read my own, right? Let me read my own.
I'll get it.
You get it, okay?
I want to import it back.
Yes, that was what I was saying.
So I'm doing that right away now.
Okay.
Documents, team leader. It's going to put
Key.
Now I have it. I have it now.
Okay.
Oh,
okay.
Sorry.
Okay. Now let's go to analyze. So we want to use male and female. If you look at the way we code, you can check the way. First of all, check the way you code. Go to click on the. You didn't code male and female.
I click on what?
No, wait. Data, go to data view. Data view.
Yes.
You are in variable view. We cannot see.
Okay.
Okay. Yes.
Let me share.
Okay. Yes. So we code one is okay. One is 1 0. Yes, that's the way we code. I think male is 1. I can't remember. I think male is 0 and female is 1. Okay, let's go. Go to analyze now. Compare mean. Want to compare the mean age between male and female. Independent. Independent. No, it's me. Okay. Yes.
This
So,
one?
yes, independent, yes. Okay, move age is test variable age. So sex is the group variable. Sex. Sex.
Yeah.
I got define sex.
Groups. 0 and 1.
0 and 1, yes. Put 0 first one, then the other one 1. Okay. Okay. Yes. You will see. So you see what I want us to see now. You will notice that the 11 test is significant here. Is 0.027, which is less than 0.05. So that shows that there's no homogeneity of variance. And I can tell you, bet you why it's like that is that look at O is the female. These one are the male because there are 95 female and 55 male. So in the sample size differ. Look at the variance and look at the standard error. Are you see now? The standard error for female is smaller. Almost like this 1 point. So it's like the male doubles the standard error of the female. So what is telling you this mean we calculated for female here is more precise. It's closer to the population mean for female than this 34 we calculate for male. Yes, I mean, because the standard error is smaller. You say that when the standard error is small, it means that the attribute is closer to the population parameter. When the standard error is larger, it means that the attribute is a little bit far. So the mean for the male, female is more precise. The precision is higher. So that is why when you now do the, which one is this? Okay, you're scrolling down. When you do the homogeneity of variance, scroll down. Scroll down is okay, thank you. So when you do the homogeneity of variance, you see that it's significant. It shows that the two, the variants are not the same. Does it make sense now? And that is why it's good whenever you are to have equal sample size, especially when you want to use some of these statistics, equal sample size. So it will ensure that the precision, level of precision for the two samples are the same. When the sample is higher with one, that one has, in all respect, it has higher precision than the one that has lower sample size. And you are comparing the two. Now,
Okay.
So it makes sense now, right?
Yeah, Dr. Dolapo, I'm still trying to, I like being practical.
Eh?
Hello, can you hear me?
Yes.
I like being practical. If you have two different sample sizes,
Yes.
and you do this comparative analysis, and there is no difference, can you still now use that as, regardless of the difference in their numbers, and go ahead and do your data analysis?
Okay, if you do it and there's no
I'm just
difference, okay.
looking for a very uncomfortable situation now where you may not have the same numbers in the two groups. And if you do the analysis and the mean is the same, and there's no significant difference in their mean, you can still go ahead and
do it. You go ahead now, people do it. You know that people are not doing. I'm just telling you the implication.
I saw a lot of it in literature.
They do it. People do it a lot. They don't even look at it. I'm just telling you the logic. So why you try to discourage it, but in some situations you cannot help it. Just like when we talk about case control, in those situations you will not be able to help it. All right, you won't be able to help it. But that is why each study also has limitation. Examiner. So the conclusion you are drawing, you have to be careful concerning that. So even sometimes when you do cross tabulation, when you see the total for one is different, but just look, is it the proportion for this thing? Can you imagine if maybe in a category now, we are talking of maybe level of knowledge, maybe you want to say people that have good knowledge or good attitude, what you do, and you cross tabulate by something like marital status, where the divorce or separated they are actually small, maybe only 10 of them or 7 of them in that category, and that 7 of them, out of 7, 5, maybe 5 has good knowledge. You know what the implication of 5 out of 7? The percentage will be high. Whereas in the category of maybe single or married, where you have 300 and maybe majority of those are there, 200 and something. And when you do 200 and something, and maybe it's half of it, over 100 like this, it will give you 50 something, and the other one is give you 70 something or 80 something. And you are not say that they are more. It's rubbish. Because when it comes to probability, if I say that probability of tossing a coin, you know, we discuss probability a lot. When we discuss, many people may not know the importance of some of those things until you are this type of scenario. No, it's the logical reasoning behind this type of scenario. Imagine if I say that what is probability if I toss a coin, it's going to be head. You will say practically say 0.5, which is 50%. Is that not so? I want response, please. I want response. You know, this is a practical discussion.
Yes.
Yeah, is that not so? You say 50%, because if I tossing a coin, what is the probability that it's going to be head? You say 50% because there are 2 sides to the coin, one head, one tail. But if I give you a coin to toss now, if we toss coin 10 times, you may see that even the 10 times can be head or tail, or up to 8 times out of the 10 can be one side. You can toss it and give you 2 may be head and 8 tail. 8 may be head and 2 tail. For you to achieve that 50-50, you need larger sample size. If you toss coin on thousands of times, you will see by the time you sum everything, the thing will be 50. Maybe that one give you 49.99 and this one 50.1. The thing will be 50-50. When you do it many a time, thousands of times. So you need larger sample size to actually get an estimate, a true estimate of something. So that is why when you are now saying, okay, level of knowledge, those ones that have higher number in that category, that percentage is given is more precise than the other one that has. So you have to be careful interpreting it. And that is why all those chi-square constabulation is more for screening. Screening, screen that is when you're analyzing, you first of all screen out what is significant. Later is good. Where is the something for this thing? I don't know if you get what I'm saying. Hello? Hello?
We're now hearing again, sir.
Yes, please stop sharing. Let me share. Okay, my this thing is okay. Leave it like that. Why is this thing not on? Okay, let me use. It's my connection that is troubleshooting here. No, this thing is not charging. That's run down. And it was full when this boy was using it. Why is it so cold? There's not even charging itself. Where's my phone? Hello, can you hear me?
Yeah.
You can hear me. So I don't know if you understand what I'm saying. That's just the logic. So I still want to go back to this year. Go back to I still want to explain that result. You're welcome. I just want to explain that result. Go back, still share that result, the last result you run. I want to bring something out. Yeah. Where is the black code for this thing? Yes, for this smile. Why is it for charging it? Yeah, it's charging now. Yes. No, it's charging now. Hello? Okay, yeah. So if you look at it, let's interpret the confidence interval. The reason I want us to interpret this confidence interval is because I don't want to say the reason, but it's different from the one we did yesterday, the outcome. So I want us to, if we can understand in another way. So is it significant or is not significant? I don't know who will comment on that. The confidence interval for this one now.
It's not.
It's not. Why?
It crosses 0.
Thank you. If you look at it, because if you look at the mean for O group, which is male, is 32.67. The mean age for, no, the O group is, is female, 32.67. The one group is male. The mean is 34.11. And the way we run it, we put 0 before 1. So we are removing 1 from 0. That we are removing the group 1 from group 0. So you are removing higher number, which is 34, higher mean from smaller mean, 32. So that is why it gives you minus. The mean difference is minus. And that is why it's giving you T to be minus. No? So I've already told you the sign doesn't actually mean anything. So it's on the left side of the T distribution because you remove this bigger value from the larger value, bigger value from the smaller value. If let's say we run it now, I will now choose 1 before 0. You will not see all this negative. T will be like that. And the difference will be this thing, positive. But it's the same value. And you will see also, because it's not going to be significant, it will still start with minus and end with plus. What it will give you is that it will say minus 1.080 to plus 3.95. You know, it's giving you minus 3.95 to plus 1.080. If you rerun it now, choose 1 before 0, you choose this group, male group before female group, you will see that, you see. So let's do it again. Because it's good, all those things is good to do it. Those are the petty things. If you don't do it, it will not stick. Let's rerun it, Dr. Balogun, let's rerun this thing. Go back to that, analyze. It's there, the icon is up there. Oh, you don't need to, you can access it from the results. Anyway, just share any of them. Okay, yes, analyze. Not report, not report. Oh. Analyze, compare means, independent. So the procedure is there, what you did before is still there. Click. Now, everything is there, just click on this sex now. Click on this sex, don't worry, everything is there. Click on this sex down, where under group variable. Where you have already put inside the box here, click on the head, click on define group, and change the upper one to 1 and change the lower one to 0. 1.
0.
0.
No, 0, 0, 0, 0.
Not 2. It will not run because there's nothing 2 coded there. You have to know the way you code it to put. Click, continue. Okay. Thank you. Can you see? Can you see that? You cannot see that the T is no more negative. And can you see? The difference is no more negative because you are removing smaller value, 32. Scroll down, compare with your head, thank you. Can you see? It's no more negative. Compare up and down. Because here now you are removing the smaller value from the bigger value. That is why the mean, the T, everything will not give you negative. But whichever, either I give you positive or negative, it's the same value. When you are quoting is the positive, you don't need to say negative. But however, scroll the head. If it is negative, you decide to write it 1.1, you write it like, you now write it different. But the confidence interval, you have to invert it. What I'm saying, you have to say, since if you change this one, the mean difference to 1.435 instead of minus 1.435, I mean the first one we run. You have to invert the confidence interval, and I say is from minus 1.080 to 3.95. Can you see? That is what give us here. You have to invert it from this. Scroll down now to see. Can you see? That is just the logic behind it. You will see that either the thing is positive or negative, the difference is positive or negative. If it's not going to be significant, the confidence interval will start from minus and cross 0 to end at plus. If it's going to be significant, there are two situations. If this is significant now, okay, let somebody read that they lost to and share it. So I explained the last time I want to explain concerning this thing. They lost to sickness we did yesterday. You know, it was significant and we removed this smaller from the bigger. Let somebody read it for us. They lost to sickness. You can share this one. Stop sharing this one, sir. So who will share that one? You have it, Prof. The software yesterday, they lost to sickness.
No.
We used to do independent t-test yesterday. The data file.
Sorry, just a little question before we proceed.
Okay, no problem. It's very has.
Now, when we start testing for equality of means, it is assumed that the data has a normal distribution.
Inequality of what? Inequality of variance, right?
No. Equality of means. The t-test.
Okay.
It is assumed that the data has a normal distribution. Am I correct?
Yes.
Now,
you assume that you use parametric test. If you assume that it's normally they use parametric test.
Okay, if it is, let's say you decide to just run the normality of data and you discover that your data is skewed.
Yeah.
Will you use the T counterpart of independent T test to check for equality of means? Is there anything like that?
Okay, if you remember, yes, because, okay, yeah, okay. Now, if you remember, you know, you were part of the how to use SPSS.
Okay.
So there we practicalize all this checking for normality, where we plot QQ plot, you remember. Is it normally distributed? We now use Kolmogorov, Spinoff, or Shapiro-Wilk. Okay, maybe we should do it now. Because these are, okay, those are, in fact, those are the assumption I just have now. Because, you know, when you ask people to come for training, there are some things that come before this. So if people are not coming, sometimes they will not understand. So I think we could do is even this same data we use, this skin lesion, we use to check for normality. So it's not necessarily, if you look at it, what this one just check is the variance, homogeneity of variance. That if you run t-test, it say do it before beside it. But if you actually want to check for normality, it's another ballgame. Yes, I'm now okay. I don't know. Before we'll go there, but I want somebody to read that day law to sickness. So let's touch it out. We'll now go. We don't close this. We still open this. Your skin lesion we used to do. Try to look at normality. How we did that time. So day law to sickness. Somebody should send it. Read it. I think it's only you and Prof that has it. That have it rather.
Sorry, it's the wrong one.
It's a wrong one, yeah. It's a
Yes,
wrong one. One sample t-test that we did. That one is for day loss of sickness. It's not sharing.
I'm looking for it.
Okay, day lock to sickness is still. Yeah. Okay, maybe I should try and share my own then. Let me look for my own. So let me share my own. I've seen my own. It's not this one. I myself
Okay, it's here.
Okay, you have seen
It's
it.
here.
Okay.
Yes, sir.
Okay, you can share. Okay. Yeah, that's it. So I want us to we first want to run it the way we run it yesterday. Those people that were not. Then we now rerun it. You will see just like the way we did today to see compare the two. Okay, go to analyze. Compare means. Independent. T-test. Day loss. Then group. Yes. Define group. Yeah, put 1. The way we did yesterday. Now go back and 2. Continue. Okay. Okay, don't worry. Before you go and share, do it again. Go back again. Before you share it, go back again. Analyze. Before you go and share the result. Do it again. Okay, yes. Let's change that group. Click on that group. Yes. Change the group. Put the other one 2 and the other one 1. Let's change it. Continue. Okay, now go and share the result with us. Yeah, scroll down. If you look at the first one, show us the first one so that people can see it. You will see the first one, the mining, the mean is 5.8, the construction is 3.73. So you will now see that the T, because you minus because mining is number one group. You minus 3.7 to 5 from 5.8, it gives you 2.067. And you can see the confidence interval, because the difference is plus. Whereas from plus to plus also, it's not cross 0. But scroll down, let's see the second one you run. The second one, okay, because you are removing bigger value from the smaller value. So even the T, everything is negative. There is the same value as per figure that is there. They mean different negative. But even when you look at it, it's from minus to minus. No, that one was from 0.523 to 3.611. This one is from minus 3.611 to minus 0.5. So it's still the same thing. I said, so you see, if it's negative, it's significant. That shows that if it's negative, that shows that the difference is negative. And it means that you remove bigger figure from the smaller figure in your calculation. So if I'm to report this one now, you don't necessarily need to put, say your distance is negative and say minus 2.7 as your t-test. Just say 2.742. And now put the mean difference, you won't put minus. But if you now come here, you have to exchange. If you want to change this confidence interval to plus, you have to exchange. The upper will become lower. It will now be plus 0.523 to 3.611, just like the way it appears up here. So that's the only thing. So if it's negative, yes, look at it. If it's negative, it's significant. If it's positive, it's significant. But if it's not going to be significant, irrespective whether the value is plus or minus, the mean difference is plus or minus, you go to start from minus and end as plus. You start from minus and end as plus. So that's just it. Logic. So the only thing is that if you want to invert the sign of your confidence interval, you have to invert the value also. You have to exchange the value. Upper will become lower, lower will become upper. You want to invert the sign. That's just it. So I think there's no further question on this issue, because it's very, very important. The issue of confidence interval. You can understand it. Okay, I think we go. You can share, stop sharing. Okay, or wait, Steph. I doubt if this will just stop sharing. Let's Dr. Balogun, share that one, that screen lesion, so that we use to. Dr. Balogun, share that screen lesion now. Let's talk about that shape of the distribution shape. Very close. Yes, that's great. Now, the way we try to see if something is normally visible or not, let's pick age here. So we want to go analyze, go to analyze. We want to explore age. We want to explore it for normality. Explore age. So no, you guys go to descriptive statistics. Under you see explore. Yes, put age there. Yes, go click on plot. Start. This statistics. Leave that one. It's already clicks descriptive. It will show you everything. Just plots. Click. No, it's okay. That one is okay. Click plot. Click histogram. By default is stem and leaf. Click histogram. And normality will plot. Thank you. Why did you remove stem and leaf? You don't need it. Leave it there. Let other people see. Why did you remove this? Okay. Okay. Continue. Okay, it's okay. Click OK. So share with us the output. You open many things. If you open many things, then you even know, okay, there, this is it. You will see that I show you the mean and confidence interval. Okay, go on. Look at test of normality. Can you see? Test of normality. Kolmogorov-Smirnov, Shapiro-Wilk. These are the two. So what it does that the SPSS has a normally distributed data inside. Comparing your data with it, is saying that it's significantly different. So it's not normally, it's far from being normal. That's what it means. There's a difference between normal and your own. So it's significantly different. So that's why the p-value, even for both type of tests, p-value is highly significant. That there's a significant difference. This one is different from normal. So this one quantify it, and you will see the skewness. If the skewness is 0, please, somebody's background is making noise. Person should move. Somebody's background is making noise. You move. Dr. Kayode, Dr. Toyi Kayode, your background is making noise. Dr. Kayode, I will remove you.
Unmute him centrally.
No, I'll remove him. You can connect back. Maybe he left the computer, is making noise. So scroll down, sir. Scroll down, sir. So you will see the normal, and let's see the histogram now. The histogram, can you see it's skewed? Look at it, can you see that it's skewed? It's not normally distributed. Though skewing is looking at it physically, show you that it's skewed, but the best way to do is to use that quantitative, the spin on all those, the test for normality to quantify it. But this one just to show you that the way it is. And scroll down. I think I've explained stem and leaf. I don't know if anybody understands this stem and leaf. If you don't understand, let me know, because I don't want to. I don't think Dr. Balogun has issue with that one, because we discuss it when we're talking about descriptive statistics, and we also discussed when we're talking about use of SPSS here. But if anybody doesn't understand, let me know. I can explain it. The stem and leaf, and histogram is saying the same thing. Look at, so you can see. Does anybody ask a question about stem and leaf? Okay, nobody. They understand it.
Let's see the figure. Let's see the diagram now.
And this is the stem and leaf.
Yes. The stem
and leaf. Do we understand it? I've explained it many times. If you understand, I will not waste time on it, so that we'll go.
Okay, sir, you can explain again.
Okay. If you look at it, you have to help me scroll to that histogram and let them see the histogram. You will see the shape of the histogram is the same thing as the stem and leaf. The only difference is that the stem and leaf just tilted sideways. Can you see now? If you look at the way the histogram go up and come down, they just tilted the stem and leaf sideways, sitting on the side rather than sitting on the base, right? That the shape is the same. But the stem and leaf, the stem and leaf give more information than histogram. Well, it's the same data that is showing us. Because the stem and leaf give us access to this data set. Like this data set now, if you want to, you can write it out and use it for analysis. This data set you see here, if I publish it with stem and leaf, you have access to the data. So what it does is that it uses the last digit as the leaf and the initial digit as the stem. If we are dealing with 3-digit number now, like height, the way we measure height, 1.72. So that last digit will be the leaf. The first digit, 2 digits will be the stem. But this one is dealing with weight. This is weight. Oh, is it weight or age? It's age, rather. It's age. And nobody is more than 2 digits in the weight, in the age. So the second digit is the rightmost, the last digit, which is the leaf. The first digit is the stem. So look at this number 1 now. Number 1 is just telling you that this frequency 1 means that only 1 is in that category, and that 1 is less than 18. Then this one 1. That 1 is 19. Can you say 1, 9? The stem is 1. The leaf is 9. That's 19. This one is 21. 21. This one, there are 8 in this category. 23, 23, 23, 23, 23, 23, 8 times. Can you see? So this one, there are 8 also. 24, 24, 24, 24, 25, 25, 25. Here, there are 11. 26, 26, 26, 26, 26, 26, 27, 27, like that. It's 16, like that. This is 28, 28, 28, then 29. There are 16. This is, we have 25 in this category, 30, 30, 30, 30, 30, up to this place, 31, 31, 31, 31, on to this place. That's what. So if you can write it out, even if there's somebody publish it, now you can write it out and enter it and run the analysis. So I think you understand now. Do we understand?
No.
Yes, sir.
Yeah, that's the way. So stem and leaf, it's the same thing with histogram, but it gives more information than histogram. So it gives you access to the value. So I think now you see this thing. Go to that QQ plot. All these things, they are just still tied to. It's okay. To show if this data set follow normal distribution or not. You know, QQ plot means quarter. No quarter at the 3 line that divide data set into 4 equal parts. The first 25%, second 25%, fourth 25%, fourth 25%. So what separates the first 25% from the second 25% is the first quarter. That's 25 percentile. What separates the middle, the second 25% from the third 25% is the median with the second quarter. What separates the third 25% from the last 25% is the 75 percentile. So you can say, when you say interquartile range, you remove 25 to 75 range. So what this one does is to plot the quartile, first, second, third, and plot it again. There's a normally distributed something data in the software. That will be the expected, while your own is the observed along the horizontal. If your own is normally distributed, you know this line is the diagonal line. All of them should line up along the diagonal. So in tug of war, if the two sides they have equal something, the thing will be in the middle. Hey, Dr. Hammer, our meeting starts by, is it?
It's not time.
Yes, so welcome, ma'am.
Thank you. Don't worry, I'm doing something else. When you are ready, I'll join.
Okay, no problem, thank you. So now, you see that there are some of them that are off the diagonal. You show that these are the ones that are those outliers. There are some outliers at the base, but more of the outlier at the upper part. That's why it's skewed to the right. If the outliers are more on the lower side, it will be skewed to the left, but it is skewed to the right. So all those things, those are the pictures showing the skewness of the data set. Dr. Attire.
Let me go out.
Welcome. Yeah. No, don't go out. I'm not saying you go. Don't go out.
Okay.
When I saw Dr. Amma, I thought maybe it's 8:30 because I know that I would stop by 8:30. We start our meeting.
No, it's not 8:30, sir.
Yes. So I think Dr. Balogun. Dr. Balogun. Is he there? Unless you unmute yourself, you cannot hear me. I cannot hear you rather. Dr. Balogun.
Yes.
So I think I've answered your question.
I'm here.
I think I've answered your question.
Yes. Can you hear me?
Yes, I can hear you.
You have, yes.
Yes. So these are the things you do to know if it's,
that's okay.
Yeah, if they are normally distributed or not before you proceed. Yeah, and look at this one also. Look at these Ox and Worcester.
Yes, sir.
Your voice is low.
Now, Dr. Dolapo.
Yes.
Hello, can you hear me now?
I can hear you.
Can you hear me?
Yeah, I can hear you.
Now, you've done this now. You've done this now. There is no, it's not the normal.
It's not normally distributed, yes.
Data.
Yes.
If you have another data, it's not normally distributed for this data. If you have another data that is talking about, let's say, age, for instance,
age,
and it is also not normally distributed.
Yes.
Hello?
I'm listening.
Are you with me?
Yes, I'm with you.
Let's say you have another data, maybe an independent sample.
Yes.
And you have another data that is not normally distributed. And
yes.
You want to compare them for equality of means. Will it still be in order to go ahead and use a t-test? Maybe because it is robust?
Okay, yeah, that's a good question. Sometimes if you look at if the skewness is not much, if the skewness is not much, you can go ahead because a t-test is a robust test. You can go ahead. And another thing you can do is that in the same data set, you can run the two. Sometimes if you run the two, both with parametric and non-parametric, you will get the same result. You see, if you can run both, you can run it with both parametric and non-parametric and see if you get almost the same result. Yes, I mean now. Like on this one here, maybe that's what we'll do tomorrow because we'll stop by 8. I have another meeting by 8:30 rather. So tomorrow I'll also do something. All this, we just give a clear example for each of those tests, the statistics. So we can actually, even all those one we use parametric, but we can actually run them with non-parametric and see and compare the results. And also the one we use non-parametric for, we can run them with parametric, with t-test and see the results. You get the picture now. So when we play around it, you'll be able to understand it better. Are we together?
Okay.
And that is why if you look at it, when you see that the data set is not normally distributed, there are 3 things which I told you. and you consider them in order of importance, the first thing, first of all, you don't rush to go and do, I'm doing now parametric, transforming. You can rely on the robustness, just like what you are saying now. You can rely on the robustness of the data, or if you cannot, you do non-parametric tests. So if you don't want to, you may transform the, but that's the last resort, which you don't even advise anybody to do, transforming the data. Because when you transform the data, the life is never remain, will never remain the same. You know, we did transformation of this one. Because if a data set is even extremely skewed, when you transform, it will just be less skewed. It may still be skewed. To a lesser extent, it will still be skewed. So that is why even transformation, the interpretation also has its own problem. Because if you do log transformation, the mean is geometric mean. And if you calculate the mean and now the geometric mean, and now convert it to anti-log, it will not correspond with the arithmetic mean of the original data. It will correspond with the median. So any other questions so that we'll just close?
Yeah.
Any other question?
Yeah, the last question I want to
so you can stop sharing. You can stop sharing this one. Stop sharing the
Let him scroll to the end. No, please let him scroll to the end.
Okay, you should scroll to the end.
Yeah, I think there's another diagram before, after the histogram.
Okay, I said you should show it. Let's quickly before.
Yeah. This one. No, this one.
Box and whisker. I wanted to say the box and whisker. This box and whisker. Look at it. It's still showing this normality. If it's normally distributed, the middle is the median. It should be in the middle of the box. That middle line is the median. But if you look at it, the upper part of the box is bigger than the lower part. It means that it's skewed to the right. There's positive skewness. It's not in the middle. So the lower end here is the lower end of the box is 25%. The upper end is 75. The whisker, the end of the whisker there is the lower value. The other one is the upper value. All this one is writing is the outliers. So if you go and check the data set now in your computer at Octobalogun, serially along the number, the 95, the one that has 95, number 95. Is it number 95? Is the sorry, number, what do I see? The data says 120. You see, go and check this data set 121. Or this one 141. Number 96. That number 96 there is the highest age, followed by this number. So it's giving you the number on your computer, the highest age. This one and this one is 120. Number 126 is the smallest age there. That's what it just showed you. But that one depends on how you sort it. So it depends on how you sort it. It's just for you to locate, help you to locate the outliers if you want to locate in the data set. Okay, I think we are done. This. Hey, Dr. Balogun, 1 minute. Your question on stop sharing and ask your question. We have only 1 minute to close. This is 29 after. Your question. Dr. Balogun, unmute yourself. If you don't unmute, I cannot hear you.
Hello, is there anything like a median test? Somebody was saying median test to compare to non-parametric, non-normally distributed.
Don't worry, we'll talk about that tomorrow. Is Wilkinson rank test also called a sign test because that's the only one that you minus. If you look at it's one sample test. That one, you know, if you repair sample test, you minus the other one from the you minus the two. Yeah. The way they did, but this one is only one sample. So they now minus the median in the population. Just like the way we use mean in the population for the other one, we do that one tomorrow. That's why they call different name. Yes, right. And that's the only one that use median. If you look at the other one we have done, none of them use median, they don't use mean also. But that's the only one that use median. You know, somebody was raising the question in is it Thursday, the lecture. I just I said that look at we are comparing the data set. Even you don't even use it, it's only one of those set that even use the media. Okay, thank you.
Okay, thank you, Dr.
Tomorrow, yeah. Okay.
Yeah, tomorrow.
Yeah.
Yeah, good night.
Yeah, good night.
everybody.
Thank you, sir.
Thank you, sir.
Thank you, sir. Good night.
Welcome, sir. Yes, sir.